So welcome to this. This is the Further Maths Support online revision session for Edexcel S3. And in this session we're going to be looking at the concepts of estimation and confidence intervals. So to deal with estimation we need to be able to understand and find this thing called standard error. We also need to make sure that we can find something called the unbiased estimator of the standard deviation as well, or of the variance, depending on what you're doing, and that's going to be quite important as we do these, so we'll look at those. We need to also be able to show that an estimator is unbiased. Now I haven't seen any questions on this, but it is stated in the spec, so that's something that using your textbooks you may want to be able to look at. We have to be able to find and use the distribution of the sample mean, and again, if your initial distribution is not normally distributed, then we need to invoke something called the central limit theorem to do that. Based on this, and this is a critical thing to do with the central limit theorem, to be able to find a confidence interval we are dealing with normal distributions. On S4 there are some ideas where we can use t-distribution instead, but on S3 we have to have the idea that our distribution that we're using to find confidence intervals are normally distributed. Okay, so we also need to be able to find, based on that, confidence limits for a normal mean with a known variance. Okay, or alternatively use the central limit theorem to get there. But we also need to be able to find the corresponding confidence interval. So you will find questions sometimes asking how the central limit theorem is useful in this case, or the importance of it, and it would be along the lines of that we need a normal distribution to find the confidence interval. Okay, so June 2010 question 3. We've got a woodwork teacher who measures the width W of a board, and the measured width X millimeters is normally distributed with a mean W and a standard deviation of 0.5. Find the probability that X is within 0.6 millimeters of W. Okay, so there's lots of ways of doing this, but if we just start formulating it in the way that the question suggests, we're going to have X is going to be normally distributed with a mean of W, which we don't know, and a standard deviation 0.5. Okay, so it says find the probability. So find the probability that X is within 0.6 millimeters of W. So in other words, X minus W in size, because it could be positive or negative, must be less than 0.6. Now, my suggested way of doing this is to actually rewrite this as being between minus 0.6 and 0.6. Now, there are other ways of doing this, understanding how moduluses work, but I think this is by far the safest way. So what we're going to do is we're going to standardize these. That seems like a very sensible thing to do. Some people don't like this because they've got W's kicking around, and we don't know that, but you need to appreciate that when we do standardize this, so we're going to have Z is equal to the X value, okay, minus mu over sigma. So the X value that we're dealing with here is going to be, let's do 0.6 first of all, so it's going to be 0.6 minus W over the mean, which is going to be 0.5. Okay, now to do this we need to realize that the mean we're dealing with is X minus W, not W, so really we should be doing this. So we can see that that's going to obliterate, and we're going to have a Z value of 0.6 over 0.5. Now if we've done the same with the negative one, that's going to give me Z is equal to minus 0.6 over 0.5. So this thing here is going to turn into the probability of being minus 1.2 is less than Z is less than 1.2. So there is some symmetry kicking on here, which is quite useful. So this is going to be the same as the probability of Z being less than 1.2 minus the probability of Z being less than minus 1.2. If we turn this round, this is going to give me the probability of Z, I'm doing this quite slowly, minus 1 minus the probability of Z being less than 1.2. So we can see that we're going to get two lots of the probability of Z being less than 1.2 minus 1. Okay, now you could work it all out bit by bit. So we've got one method mark really. Your method mark kicks in here. So what we now need to do is to work that out. Okay, so 1.2 is 0.8849. So the probability that we're looking for is going to be two lots of that minus 1. okay, which is going to give me 0.7698, and that's where we're going to get our second mark in this particular aspect. Okay, so it then says the same board is measured 16 times and the results are recorded. Find the probability that the mean of these results is within 0.3 of W. So again, we've got a similar idea here where we're going to be forming x bar minus W in magnitude must be less than 0.3. So again, we need to understand the distribution of x bar. So x bar is going to be a normally distributed thing. Now the mean is going to be the same, it's going to be W, but actually the standard deviation of x bar, we're going to need to use the standard error. And the standard error, so standard error, is equal to sigma squared over n. Okay, so in this particular case, we're going to have 0.5 squared over 16. So that is the distribution of the sample means. Okay, we're not using central limit theorem here because we are told that it's normally distributed. Okay, you only use the central limit theorem if you don't know that you're normally distributed. Okay, so we're going to do exactly the same idea here. So this is the probability of being between minus 0.3 and 0.3, and again we're going to standardize, but again we're standardizing x bar minus W. So in other words, Z is going to be 0.3, going to look at the positive one, minus W, which again gets obliterated, divided by 0.5 divided by 4, because I'm looking at the square root of 0.5 squared over 16. So my positive Z value is going to be a Z value of 2.4. And I can clearly see that my negative one is going to be minus 2.4. So this again turns into the probability minus 2.4 is less than Z is less than 2.4, and it's exactly the same argument as before. So this is going to be two lots of the probability of Z being less than 2.4 minus 1. Okay, so we just need to find that Z value. There we go, 2.4. So it's going to be two lots of 0.9918 minus 1, and that's going to give me 0.9836. So let me show you where these 4 marks are allocated. Okay, so you get 2 marks. Well, you get 1 mark for getting the distribution correct in the first place by understanding the distribution of the sample means, and your second 2 marks are going to be for standardizing correctly and working out what we need to do in terms of probabilities, and then only 1 mark, an accuracy mark, for getting your correct answer. Okay, so in part C, we're asked to find a 98% confidence interval. Okay, so to do a confidence interval at 98%, you need to realize what's really going on. So we've got a distribution. Okay, it's normally distributed with a mean in the middle of W, and the 98% confidence interval really means that we are looking at the middle 98%. So that's going to give me a probability value, let's call it P, of 0.99, and at the bottom end it's going to give me a P value of 0.01. Okay, so the mean is in the middle. So what we're looking for is our confidence interval. Now there's a formula for this, and it's going to be x bar plus the corresponding Z value that we're going to be dealing with times by the standard error of what's going on. Okay, and that's the standard error that we're using. Notice I'm using sigma squared, not s squared, and the reason I'm using sigma squared is because I am given the standard deviation. So I've got a known variance, and I'm using x bar. It should be plus and minus, sorry. I'm using x bar because it's based, your confidence interval is based on the sample that you've found. So this is going to be 35.6, that's what your sample mean was for this. I know that because I'm told it. Plus and minus the Z value. So there is a Z value corresponding to P equals 0.99 in your inverse probability tables. That's going to give me a Z value of 2.3263. I'll show you how to look up that in a later question. But that's going to be 2.3263 times by the standard error, which we worked out before as being 1/8. So your confidence interval, if you work out the subtraction, will give you 35.3, and if you work out the addition, that will give you 35.9. So again, 4 marks for this. How are they worked out? Well, you get 1 mark for getting the structure of the confidence interval correct. So we're looking for this sort of structure. okay, x bar plus or minus a z value times the standard error. Okay, now it doesn't have to be the correct z value to get the method mark, but obviously it would be good if you did. You get a B mark, an independent mark, for using the correct z value, and then you get 2 accuracy marks, one for working out each endpoint on the confidence interval. Okay, so moving on to another question, June 2011, question 7. Now I'm only looking at parts B and C here in this particular one. But Roastie's coffee is sold in packets with a stated weight of 250 grams. A supermarket manager claims that the mean weight of the packs is less than the stated weight. She weighs a random sample of 90 packets from their stock and finds that their weights have a mean of 248 and a standard deviation of 5.4. Okay, so we are asked again to form a 98% confidence interval for this. So we've got all of the key factors here. So we need x bar plus or minus the corresponding z value over, now in this particular case it's going to be s squared that we're dealing with. Okay, and the reason we're using s squared here over n is going to be the square root of that because it's the standard error we're looking for. The reason we're using s squared is because it's a standard deviation from a sample. Okay, now don't need to worry too much about that, but we will need to a bit later on. So this is going to give me the mean, which is 248, plus and minus. Now the corresponding z value, I'll just show you here, is going to correspond to 99%. So it's going to correspond to that z value there. So that's why I know it's 2.3263. So that's going to be 2.3263, and it's going to be multiplied by the standard deviation, so it's 5.4, over the square root of the sample size. Okay, so again, another way of writing your confidence interval is x bar plus or minus z times by s over root n. Okay, so we can calculate that, which is fine, adding and subtracting. Now generally we give this to 3 significant figures, so we're looking for 247 to 249. Now if you don't use the correct z value, then you run the risk of getting the wrong confidence interval. So if you use 2.33 for instance, then that can be problematic. Okay, now the reason I've chosen this question is because of the stated weight. Okay, so just make a note that the stated weight is 250. So it says, state with a reason the action you should recommend the manager to take over the weight of a packet of Roastie's coffee. So let's look at this. Your confidence interval is 247 to 249, and we're claiming that the mean should be 250. So in this particular case, you can see that the confidence interval is wholly below what it should be. Okay, now this is similar in a way of doing a hypothesis test. So because it's wholly below the population mean, that's what we're looking for, 250, we've got some evidence to suggest that based on this sample, then the weight of the packet is under 250 grams, and that's because the confidence interval is completely below 250. So I would be asking the manager to investigate. Okay, so I'd be asking him to investigate that stated weight is too high, or something along those lines. Okay, there are other ways of doing this. Confidence intervals is one way, hypothesis testing is another way. So this is a way of using a confidence interval to maybe do some form of a hypothesis test. Okay, so hopefully that's covered a little bit about how confidence intervals are formed. Again, the key features are things like understanding why we have to use the central limit theorem, and again a lot of that is because we need a normal distribution to be able to find confidence intervals in S3. Okay, so make sure that you are fully aware about how they work.